Hey, and welcome to Trig. This is section 2.4, Sum and Difference Formulas. Alright, so here are the sum and difference formulas for sine and cosine, and we'll find the sum and difference formulas for tangent in a little bit. They're also found on page 236 in your book. Alright, so what's nice about these? Why do we have to learn them? Well, first of all, the nice thing about these is if you're trying to find exact values for sine and cosine, but you have a number that's not on the unit circle, if you can find two numbers that either add to that number or subtract to that number, then you should be able to find the sine and cosine values exactly. So here's what I mean. Let's go through an example. So find the exact value of cosine of 75 degrees. If you look at 75 degrees, is it on your unit circle? It's not. It's somewhere in here, so we don't have the exact values of sine and cosine. Okay, so what we're going to do instead, and we want to find exact values, not decimal approximation, so we can't just type into your calculator and be done. We're looking for the exact values of 75 degrees. So you want to say, what numbers can I add or subtract to get to 75? And what I'm specifically looking for are the degrees that are on the unit circle. So if I look and say, well, 30 plus 45, if I add those two together, that's 75. So I can rewrite this as cosine of 30 plus 45. And yes, of course, you can always switch them. It doesn't really matter. Alright, so now I've done cosine of 30 plus 45. If we just go back up, we say, well, we're dealing with cosine, and we're dealing with addition of cosine. So it's cosine alpha, cosine beta, minus sine alpha, sine beta. So these are all just slightly different, but it's just cosine, cosine, minus sine, sine. Okay, so we can say this is the same as cosine of 30 times cosine 45, right, minus sine 30 sine 45. Okay, so really we just go, you find the two numbers that add to 75, and then you break it apart using these formulas here that we have again on page 236. Okay, so now let's find cosine of 30, cosine of 45. So we have cosine 30 is square root of 3 over 2, square root of 2 over 2. Okay, so this would be square root of 3 over 2. This one is square root of 2 over 2. And then sine of 30 should be 1/2, and this should be square root 2 over 2. And if we subtract them, we get this. And then we can go through, multiply these together. Since it's multiplying, it should be square root of 6 over 4 minus square root 2 over 4. And this right here is the exact answer. Okay, no decimal approximations, we have an exact answer, and this is it. Obviously, it's not going to be super nice like the other ones were, and otherwise it would be included in the unit circle, but if we want to find the exact answer, this is it. Okay, and again, if you wanted to rewrite it maybe a little bit simpler, you could say square root of 6 minus square root of 2 all over square root of 4. Either way is okay. Alright, so here's the next example. Find the exact value of sine of pi over 12. Now, if we go back and say, is pi over 12 on here? No, but it's half of pi over 6, right? So how can I get to pi over 6? Well, let's see. I need something that's over 12, and are either one of these over 12? Not really. So maybe we can just kind of say, let's see if we can rewrite some of them. Okay, so pi over 12 is the same as pi over 3 minus pi over 4. And you say, I don't believe you. Okay, fine, let's get common denominators. I'll multiply this one by 4, multiply this one by 3, and I get 4 pi over 12 minus 3 pi over 12. 4 pi over 12 minus 3 pi over 12 gives you 1 pi over 12. So here are the two numbers that I want to subtract. So I can rewrite sine of pi over 12 as sine of pi over 3 minus pi over 4. So even though we looked at this and I said first, well, let's use pi over 6. Maybe that will be helpful. Not quite. Okay, so we want to use this subtraction. So now we just have to go and find the difference formula for sine. Difference formula for sine, oops. Go back to here. It's sine alpha minus beta, so it's sine A, cosine B, cosine A, sine B. Okay, so sine alpha, so it's going to be sine pi over 3 cosine beta, so it's going to be times cosine pi over 4. Notice how this pi over 4 is positive, even though there's a subtraction here. It's alpha, beta, so we're just doing that. The subtraction kind of comes and gets taken care of here. Okay, so now it's going to be minus. We go back and you say cosine alpha times sine beta. Okay, so this is going to be cosine pi over 3 times sine pi over 4. Alright, and then we just have to plug those back in using your unit circle. Alright, so I think the hardest part about this whole thing is just keeping track of which one is alpha, beta, cosine, cosine, plus or minus. All this stuff is the hardest thing, is just to remember it. After that, it's just plugging it in and getting your answers, right? So, pi over 3 is square root of 3 over 2. Pi over 4 is square root of 2 over 2. Minus cosine of pi over 3 should be 1/2. And this one should be square root 2 over 2. Okay, so this is going to be, again, square root 6 over 4 minus square root 2 over 4. Alright, and again, we can do the same thing, square root 6 minus square root 2 all over 4, and then that would be your answer again. So we have the exact same thing. Let's see, sine value of pi over 12 is the same as cosine value of 75, which means they're probably opposite angles, or they're probably complementary. Those two angles would add up to 90 degrees. Okay, so now let's find the exact value of sine 42 cosine 12 minus cosine 42 sine 12. So really what this question is asking you is, if I can rewrite this, instead of going the direction we did here, where we said have this nice simple one and make it a little more complex, can we have the more complex one and just write it back to where one value? Okay, so is it sine or is it cosine? I see a minus, so we're looking at a sine cosine minus cosine sine, right? So we go back to the original, sine cosine minus cosine sine. I think it is this one right here. Let's just double check. Sine cosine minus cosine sine, right? Sine cosine minus cosine sine. So really that's going to be sine, the first one that we have, minus the second value we have. Okay, so it's going to be sine of the first value we have, 40, minus the second value we have, which is 20. And yes, we can write it a little bit simpler. That would be sine of 28. And it's probably it is in fact degrees. I just can't write in the degrees here because it's always just so annoying to do. Okay, there you go. And now here are the sum and difference formulas for tangent. Way more complex because it's, well, I guess I shouldn't say way more complex. It's just got division in it, which is just a little more annoying. Okay, so let's simplify tangent theta plus 3 pi. Okay, so we go back here and we say tangent A plus B. It's going to look like this one. All right, so we're going to say, we can say theta is A, 3 pi is B. Okay, so we have tangent theta plus tangent 3 pi. Let's say this is tangent theta plus tangent 3 pi divided by 1 minus, and we've got tangent A times tangent B. So we've got tangent theta times tangent 3 pi. Alright, so we've successfully rewritten this now to what we needed to write it as, right? Okay, good. So, then what can we do in order to do this one more effectively? Can we simplify it? Well, of course we can. Tangent 3 pi, remember, 3 pi is just 1 pi, 2 pi, 3 pi. That's over here, and it's always sine over cosine. So 0 divided by -1 is going to be 0. So tangent of 3 pi is just 0. So we can say this is the same as tangent theta plus 0 over 1 minus, well, this is 0 times this thing is going to be 0. So we can say that's just tangent theta, right? Which is not really surprising because we know that this thing is going to be, if we go around 3 pi, it's going to give you the same value as it did before. All right? And we have two more. We got this one and the next one. So write cosine arctangent of 1 plus arc cosine x as an algebraic expression. Okay, so here's what we're going to do. Kind of going back to our original one right here, we have cosine and we're adding two things together, right? We're adding two things together, so you can kind of think of this one as alpha and this one as beta, okay? So, then we can say when we're adding cosines, we can say this is the same as cosine alpha, which is arctangent of 1, times cosine of beta, which is cosine of arc cosine of x. Okay, and then we're going to subtract sine times arc tan of 1 times sine of arc cosine of x. And I really don't need this parentheses here. I'm just going to get rid of it. I don't know why I put it in there. Alright, so really all we did was we just replace this with alpha and this with beta, and I just said arc tangent of this one, arc cosine goes here, and I did the same thing with these two. Okay, so the nice thing about cosine and arc cosine is they are reciprocals, meaning that this is just 1. Okay, so we will have that one, and sine, arc, cosine, and that's what we have so far. So we kind of made this one a little bit simpler. Okay, so far so good. Okay, so now to make this a little bit clearer, what we need to do is we need to get a triangle. Okay, we're going to actually get 2 triangles. That one's okay, and we'll get the other one to be solid. Okay, good. So let's just label this one, this angle alpha, and we'll label this angle beta. Okay, these are right triangles, and so we know alpha is going to be arctangent of 1, which means if I take sine over cosine, or opposite over adjacent, right, of a right triangle, we know that they have to be 1, so I'd say this one's 1, this one's 1, and that means it's a 45, 45, 90 triangle, which means this should be square root of 2. Okay, and then for beta, we know that arc cosine is x, right? So that means cosine is adjacent over hypotenuse. So that means we have x, and we have 1 here, which means then this one, if we use Pythagorean theorem, we'd have the square root of 1 minus x squared. Okay, use the Pythagorean theorem to figure out this one. This one squared minus this one squared gives you this one. Okay, so we have some of these values, right? So then what we can say is if I want to find cosine of arctangent of 1, say cosine of this, and I get cosine is adjacent over hypotenuse, right? So this whole thing, now because I'm just taking cosine of this triangle, of this angle, right, because this one's alpha, so it's adjacent over hypotenuse, which is this whole thing right here would be 1 over square root 2, right? This one we know is 1. Sine of arctangent of 1 is this one again, right? So we're saying sine, which is 1 over the square root of 2. And this one is sine of arc cosine. So we're saying sine of arc cosine is this one over hypotenuse. So that's going to be the square root of 1 minus x squared over 1. Alright, so now what I'm going to do is I'm just going to move some of my triangles over here to maybe clean this up a little bit more. Let's see if I can maybe just move it over there. Okay, and we will try and write this whole thing as these are multiplied together, subtract, multiply those together. So I have 1 over the square root of 2 times 1. Let's just leave it as 1 over the square root of 2 for now. Minus, we have 1 times the square root of 1 minus x squared, all over square root of 2 times 1, which is square root of 2. Okay. Oh, sorry, this isn't 1, this is x. Whoops. It's an x because we have cosine times arc cosine. They cancel each other out. We're left with just an x, so that means this is an x, not a 1. So then if we just combine everything, because we have common denominators, we can say this is the same as x minus the square root of 1 minus x squared, all over square root of 2. And we could rationalize the denominator, but I'm just going to leave it like that because that was fairly complicated for you to probably follow along. Alright, and last one. And this is an application from calculus. Let me just move this down so you can see it real quick. There we go. So this is something that you'll see in calculus. We're going to verify that this is the case. We'll kind of get to what this means when you get to calculus, but basically we're saying if you have some value for x and you have some very small value for h, what is that going to look like? Okay, and we'll get to why we do this and why it's so important and why we have used it for so many years and why Isaac Newton was really, really ingenious for that, or did he steal someone else's ideas maybe and take the credit for it. But for now, we're not going to worry about that. Okay, so we're going to use what we know about the sum and difference formulas to show this one is to go from here to here. Okay, so what we're going to do first is we are going to take the sine x plus h and we are going to expand it out. Okay, so let me show you what that looks like. So using our formulas, right, we have sine alpha plus beta, or on page 236 again, it's u plus v. So we can say this is the same as this part right here. So I'm actually going to write this part. We'll do it in red. Okay, so I'm going to just expand this thing using our sine sum formula. Okay, so we can say that is sine x cosine h plus cosine h sine x, and then we have this as minus sine x all over h. Okay. Did I do that right? X, H, X. Oh, I think I should have this the other way. It should be X and H that way. Okay, let me just redo this part right there. There we go. Nice and bold. Because I think I just did this the wrong way. So it's sine X cosine H, right? And then it should be plus cosine X sine H. There we go. That's better. Minus sine X all over H. Okay, good. So now what we have to do is, let's say, do you see how both of these have a sine X? I'll underline them in blue. This one's got a sine X, and this one has a sine X. So what I'm going to do is I'll write sine X, parentheses, I've got cosine H minus 1, right? I just kind of combine those two. And then I have the rest of it as plus cosine X sine H all over H. Okay, now does that look like this? Not quite. Not quite. But I kind of distribute this H to both of them. Sure, so that means I can, and I'm going to write it over here, we can say this is cosine H times sine, oops, hold on a second. Okay, so we got cosine, I'm actually going to start with this part first, so I'm actually going to delete this just for a second here. And I'm going to do this part first. We've got cosine X, and then we have sine H over H, because I can do the sine H over H at any time, so I can put that in parentheses, which gives us this one right here. Okay, so I've got this part done. It looks like this one. And now I just have to get this first one to look like this. So it's 1 minus cosine H, and I have cosine H minus 1. So it's like I have to factor out a negative here, which means I need to put the negative out in front, which helps because I've got a minus. So I can say minus, and it's just switching the order. We can say sine X, and it's 1 minus cosine H over H. Alright, so notice how the H's kind of stick together here and stick together here, and then we can say, see how we have this thing, it actually turns into this thing. Why do we have to do that? Well, you'll see in calculus a little bit more of the application, but here's just a good reason for using the sum and difference formulas to find something else out that you will eventually do in calculus. Alright, so I know that's kind of a longer video, but here are some very good examples on the sum and difference formulas. Again, if you forget any of them, they're on page 236 in your book.